All right, we're going to talk about enthalpy. Enthalpy, we use the letter H to represent because that makes so much sense. Heat is Q, enthalpy is H. Go figure. And of course, if we have a delta in front of it, that means the change in enthalpy. Here's the definition of enthalpy. It's the sum of its internal energy plus the product of pressure and volume. Okay? So, energy, the internal energy is equal to heat plus work. And we're calling all of this enthalpy. So basically, most cases, you're going to be using constant pressure. So you can take this piece out, which means the enthalpy is going to be equal to the energy. And if you do a little fancy math, you can cancel the work out, which means enthalpy ends up being equal to heat for the most part, at least for what we're going to be using it for. If you get on into physical chemistry, it may be different, but for now, we're going to use this. So this first question is just kind of silly, because it's telling you that 1 mole of butane is going to produce 2658 kilojoules of heat. Heat is Q. And it's going to do 3 kilojoules of work. We know up here Q plus work is equal to the change in energy. And that's what the question is asking. So if this is Q and this is work, if we add them together, why can't I add? I'm multiplying. This is like the 3rd time I've done this. 8, 9, 10, 11. 5 plus 1 is 6. 6, 2. 2, 6, 6, 1. Plus, if you read in the question, it tells us it's producing the energy. That means it's being given off. So it's negative 2661. That is equal to heat plus work. So this value is our delta H, E. This value was the delta H. So the answer is number 1. All right, a couple things to remember. The value of delta H for a chemical reaction is the amount of heat absorbed or evolved in a reaction under constant pressure. If it's absorbed, it's going to be endothermic. We've already defined endothermic and exothermic. Endothermic is going to be a positive enthalpy. Exothermic is going to be a negative enthalpy. All right. Now we're going to do an equation. I'm going to switch colors. I'm tired of purple. All right. If we have 2 of product or reactant A, it's going to produce product A. And that energy is going to release 51 joules of energy. It says, what is the heat associated with the reaction of 6 moles? Well, we know 2 moles of A gives us negative 51 joules. So if we're talking about 6 moles of A, how much energy will that be? Cross multiplication. So we go do the math. 51.0 times 6 divided by 2, 153 joules. The energy is being given off, so there's your answer. All right, here's another example. An LP gas tank in a home barbecue contains 13.2 kilograms of propane. Calculate the heat associated with the complete combustion of all the propane. All right. Well, it tells us that 1 mole of propane is going to produce 2,044 kilojoules. We got to figure out how many moles of propane we have. We have 13.2 kilograms. 13.2 kilograms is going to be 13,200 grams. So the first thing we have to do is change that to moles. How do I change that to moles? Well, I got to know the molar mass of propane. Carbon's 12 times 3 is 36 plus 8 hydrogens. It's 44. I should have remembered that. So we're going to take 13200 divided by 44, and we're going to get 300 moles of propane. Now, what did our problem tell us? 1 mole, we know it's 1 because there's nothing in front of it, makes 2,044 kilojoules. All right, so if we have 1 mole, we create 2044 kilojoules. 300 moles is going to make X number of kilojoules. And we cross multiply. So we're going to do 300 times 2044 divided by 1. $613,200 kilojoules. We got 3 sig figs, so we would write that like that. All right, next question. Ammonia reacts with oxygen according to this equation. 4 moles of ammonia and 5 moles of oxygen will produce 906 kilojoules. Calculate the heat if we have 155 grams of ammonia. All right, we know 4 moles is going to make negative 906 kilojoules, right? So how many moles of ammonia do we have? We have to change grams to moles. To do that, we divide by 17 grams in 1 mole. 155 divided by 17, I get 9.12 moles. How much energy is that? Negative 906 times 9.12 divided by 4. That means 2,065 I'm just making sure, and it's negative because there's that negative there. Kilojoules. Is that one of my choices? Well, they're written in scientific notation. So 3 sig figs, 1, 2, 3. Good enough for me. Next one. What mass? Now we're going to solve for moles and mass. Okay. Here we're talking about butane. Butane has 4 carbons. So we know that 1 mole of butane, 2658 kilojoules. We want to know how many moles, and then we'll convert that to grams, will be necessary to produce 1,500 kilojoules. Because 1.5 times 10 to the third would be 1,500, right? All right. Simple. Cross multiply. We're going to do 1,500 kilojoules times 1 mole is equal to negative 2658x. And so we get negative 1,500 divided by negative 2658.564 moles. Now, is it asking us for moles? No, it wants grams. How do we go back from moles to grams? That's right, we multiply by the molar mass of butane. Molar mass of butane. See, here we'll ask Google. Okay, Google, what's the molar mass of butane?
The molar mass of butane is 58.12 grams per mole.
I don't know if you all heard that, 58.12. That's how I've been doing this since I'm at home. If only I could have Google Home at work. It would make it so much easier. But we've asked Siri on the laptops or the iPad, so it all works. So 0.564 times 58.12, 32.8 grams. Okay? So this should set you up in order to do the section called enthalpy in your Mastering Chemistry online Pearson stuff. Okay? So go ahead and try that next part.